Okay, we're now in introduction to the book. I think we just finished the introduction to the book, excuse me. Synchronicity, Through the Eyes of Science, Myth, and the Trickster by Hon Combs and Mark Holland. And this is the proper cover for the third edition. I think the original was 1942. And that one was, I think it was 1990. Oh no, I can't. I get the dates wrong. It doesn't matter. Let's look it up. Anyways, part 1 of Synchronicity and Science. An immense impulse was now given to science, and it seemed as if the genius of mankind, long penned up, had at length rushed eagerly upon nature and commenced with one accord the great work of turning up her hitherto unbroken soil and exposing her treasures so long concealed. It seemed, too, as if nature herself seconded the impulse, as if to call attention to her wonders, and signalized the epic. She displayed the rarest of the most splendid and mysterious of all the astronomical phenomena, the appearance and the subsequent total extinction of a new and brilliant fixed star twice within the lifetime of Galileo himself. J.F.W. Herschel. Anyway, Herschel's my middle name for what it's worth. The Cabinet of Natural Philosophy. 1. Bus tickets. Science discovers synchronicity. We thus arrive at the image of a world mosaic and cosmic kaleidoscope. Hey, I could say that, I'm damned. Which, in spite of the constant scufflings and rearrangements, also take care of the bringing like and like together. Paul Karmer does get their salaries, something like that. The bus ticket. The first detailed investigations of what we today call synchronicity are undertaken early in this century, the 20th century, as the Australian biologist Paul Kammerer, I say by the Australian, these words just show up, they're not even there. I can't help it. It's like I'm tortured day in and day out, and I'm going to share my torture with anybody else who will hear it. So you know what it's like to have MS and all the symptoms of it. He approached the meaningful coincidences strictly as objective physical phenomena. He was fascinated by events that repeated themselves in time or space too frequently to pass off as mere chance. Suppose, for example, that on a particular day you notice that your bus ticket bears the same 2-digit number as your theater ticket, which in turn is the same as the number on the clock room ticket given you later that evening at the restaurant. Afterwards, you go to a party held at a street address, which turns out to be the same number again. This is precisely the kind of unlikely sequence of events that intrigued Kammerer. In pursuit of such sequences, he spent hours in public places watching people pass by and noting the insistence of particular hats, articles of clothing, parcels, and so on. He analyzed the observed sequences in detail, categorizing them into first, second, third, and higher order series. Additionally, he developed a complex classification system which emphasized the structural relationship in each coincidence as homologous, analogous, and so on. So homologous, analogous, and so on. Kammerer realized that such coincidences implied an expanded vision of reality. In the fashion of a good experimental biologist in the no-nonsense age of Victorian science, he held the view that such sequences evidenced a precisely undiscovered objective principle of nature, a natural philosophical law which he named the law of series. This law expressed a special kind of inertia according to which similar events repeat themselves, spreading like ripples on the surface of water. Our example begins with a number on the bus ticket would be considered a series of the fourth order because it involved a sequence of 4 occurrences of the same 2-digit number. In addition to sequential recurrences of events, Kammerer also compiled series of parallel and concurrent events, those that occur simultaneously or nearly so. In describing the number of such parallel events, he used the term power. One of the authors experienced a concurrence of the third power some years ago while he was on the way to pick up a book, The Psychology of Consciousness by Robert Ornstein, previously loaned to a friend. As he started out the door of his office, a colleague engaged him in a conversation about an article in a magazine, Human Nature, a magazine edited by Robert Ornstein, that has since gone out of business. He commented to his colleague that he was in fact at that moment on his way to pick up a book written by Ornstein. His attention was then caught by a package that moment before it arrived in the mail. It was from the Office of Human Nature magazine. Upon opening it, he found enclosed a copy of The Psychology of Consciousness, a gift copy for subscribing to the magazine. The 3 events in this third power set were: first, the fact that he was on his way to pick up Ornstein's book; second, that he was sidetracked into a conversation about the magazine that Ornstein edited; and third, that a copy of Ornstein's book arrived in the mail at that moment. This whole business also unfolded 2 concurrences of the second power. One was the presence of the book in the conversation with a colleague at the very time of its arrival in the mail. The other was the presence of the magazine in the conversation, corresponding to the arrival of the book from the magazine offices. This example gives us a sense of the Gordian knot quality of many such coincidences. Several coincidences seem to be unfolded together, so that one does not know just where to start or stop counting them. Kammerer's elaborate set of categories were intended specifically to handle just this sort of complexity. The author's experience is similar to many of those reported in Kammerer's book. For the most part, they are trivial, though they have a certain quaint appeal that arouses our curiosity. From the age of 20, Kammerer kept a log of such coincidences, which culminated in his book Das Gesetz der Serie, in English, The Law of Series, published in 1919. The book is divided into two major sections. The first is devoted to the meticulous classification of type of consciousnesses. It includes exactly 100 cases, beginning with what Cloister, I guess I pronounce it, calls a motley collection of instances. Under various headings, such as names, words, numbers, letters, dreams, and disasters, this is followed by a discussion of the morphology of series, plural, where Kammerer actually makes a distinction between the order of series, the number of similar events sequenced in time, and its power, the number that occurred more or less at the same time. These are classified according to the number of parameters they share. For instance, the following concurrence, case 10 in his book, involves 6 parameters, and it is a story of 2 soldiers, both 19 years of age, both born in Silesia, though they did not know each other, both volunteers in the transport corps, both admitted to the same military hospital in 1915, both victims of pneumonia, and both named Franz Reichard. The second portion of his book, Kammerer gives a systematization of series of coincidences as cyclic, phasic, or altering, pure or hybrid, homologous or analogous, inverted, and so on. The value of all of this fine-grained taxonomy seems questionable. Unlike the biological specimens with which Kammerer was accustomed to working, meaningful coincidences do not seem to lend themselves to definitive categorization. Despite this difficulty, Cloister makes a favorable comment that, however justified skepticism may be, the first attempt at the systematic classification of causal serial events may, perhaps, at some future date find unexpected applications. Kammerer closes the first part of his book by stating, "We have found that the reoccurrence of identical or similar data in contiguous areas of space or time is a simple empirical fact which has to be accepted and which cannot be explained by coincidence, or rather which makes coincidence rule to such an extent that the concept of coincidence itself is negated. Here, Kammerer touches on the most essential features of his study of coincidences. The reoccurrence of identical or similar data. In fact, virtually all of Kammerer's cases involve repetition of the data. Throughout, he emphasizes the trend for like to attract like. As we have already seen, however, some of the most instructive examples of synchronicity do not display this quality of similarity, but involve rather the coincidence of meaning and idea that we will develop in detail in part 2. Most of the cases of Kammerer's book are in themselves insignificant, and virtually all fall into the category of curiosities. In spite of this triviality, though, in spite of his obsessive predilection for analysis, Kammerer was able to see through this motley collection of syncretic exotica to a deeper sense of unity, as implied by the question that the beginning of this chapter, as implied by the quotation at the beginning of this chapter. This must not have been easy, for as Chung Tzu said many centuries ago, Tao is obscured when you fix your eyes on little segments of existence only. It is the second major part of the law of series. Kammerer gets down to theoretical business. Here he develops the idea regarding the nature of coincidence. Like Carl Jung and Wolfgang Pauli, who were to follow Kammerer's postulated and a causal organizing principle, which he placed on par with causality itself. This causal factor draws like and like together. It is a special kind of gravity that operates in terms of form rather than in terms of traditional physical variables such as mass and energy. Events similar in form mutually attract each other to yield a recognizable series of events. Kammerer believed that clusters of recurrent events propagate in cyclic fashion, like waves of water. Only the peaks of the waves are visible. The troughs are hidden from view. Thus, for example, gamblers experience a run of good luck at each peak. At other times, they do not do so well. In support of this view, Kammerer viewed previous theories as periodicity. These included the Pythagorean symbolic use of the number 7. For example, there are 7 musical notes in an octave, and then they repeat. Gauss revolving good and bad days, and Freud's belief in 23 and 27-day cycles that combine to affect behavior. As a biologist, Kammerer felt that the cycle behavior was characteristic of natural processes. In general, a major sector of modern systems theories, known as chaos theory or chaos dynamics, is devoted in part to just those types of periodic processes that so fascinate Kammerer. Turbulent Mirror by John Bridges and David Peat is a highly readable introduction to this mathematical approach to processes that appear random on the surface, but on careful scrutiny are found to follow certain general patterns specified by mathematically defined attractors. Some of these, known as chaotic or strange attractors, depict processes that are entirely unpredictable and in short run by and a long run show periodic fluctuations. An example is the weather. Short-range predictions of the weather are, as we all know, notoriously unreliable. This is because of the large number of factors that interact to affect it, and also because even the smallest of factors may exercise inordinately large influences on the final result. One day it rains, the next day it's dry. On the other hand, long periods of wet weather that last weeks, months, and even years are followed by similarly long periods of dry weather. Luck in gambling seems to follow this similar course. Periods of good luck are followed by periods of bad luck. Though gamblers do not always win during streaks of good luck, nor do they always lose during streaks of bad luck, it is worth noting that the founders of chaos theory were more than casually intrigued by the behavior of the roulette wheel. Sessions with the computer were sometimes followed by trips to casinos for field tests. Chaos theory does not explain processes such as the weather or behavior of the roulette wheel, but it does demonstrate that mathematical analysis is capable of describing seemingly random processes that look very much like those which interest Paul Kammerer. Many of these, like the weather, are driven by natural forces that have little to do with the unique quality of personal significance so characteristic of the instances of synchronicity that would later engage and hold the attention of Carl Jung. Even without the benefit of modern chaos theory, however, Kammerer's cases, virtually all which involve repetitions of one sort or another, were more than a little vulnerable to explanation as chance alone, or perhaps we should say to the complex interaction of unknown factors that have little or no significance for the individual. Although, as mathematician Michael Schellis clearly points out, probability and statistics have at best a questionable application in such matters. Each of us is nonetheless bound to experience a certain number of improbable combinations of events. To make too much of these might be like watching clouds and making a fanfare over those few that have remarkable shapes. Both Schellis and Jung criticized Kammerer on such grounds, though Einstein commented favorably on his book, saying that it was original and by no means absurd. See Appendix 2 for an in-depth comparison of probability and synchronicity. It was Paul Kammerer's fate to be criticized. He was one of the last Lamarckian evolutionists. These biologists believed that the individual experience of an organism could influence its offspring. A standard example is that a lion that develops great running speed by virtue of its own unique experience might pass some of this acquired skill along to its cubs. Such notions were in stark conflict with the dominant mechanistic biology of the early 20th century and put Kammerer in direct conflict with the leading biologists of his day. One of his chief opponents in battles of theory was the great Darwinian William Batson, father of Gregory Batson, the well-known biologist, philosopher, and founder of the double-blind theory of schizophrenia. Seeking support for his Lamarckian idea, Kammerer had acquired a remarkable knack for experimentation with reptiles and amphibians. His specimens, however, were lost during World War I, and the last one preserved, a midwife toad, Alites abstractius, I guess abstractius, was found to have been tampered with. In September of 1926, personally humiliated and his reputation in shambles, Cameron took a stroll up an Austrian mountain path and shot himself in the head. His life story is told in a fascinating biography written by author Kolster, The Case of the Midwife Toad. This book contains an appendix, The Law of Seriality, which is the best introduction to Kammerer's idea of synchronicity available in the English language. Das Gesetz der Serie has not been translated. This pops up. I guess now it's 2. So it's the part 2 of Synchronicity in Science. Synchronicity in the House of Physics. And I must quit for a little bit because my shoulder blades are burning. Alright, here we go. Synchronicity in Science. Part 2, Synchronicity in the House of Physics. First, he conceived from the depth of his being of something neither mind nor matter, but rich in potentiality. It was the medium in which the one and the many demanded to be most subtly dependent upon one another, in which all parts and all characters must pervade, and be pervaded by all other parts and all other characters, in which each thing must seemingly be put in influence in all other things, and yet the whole must be no other than the sum of all its parts, and each part an all-pervading determination of the whole. It was a cosmical substance in which any individual spirit must be mysteriously at once an absolute self and a mere figment of the whole. Elof Stapleton, Star Maker. As we saw in Chapter 1, Paul Kammerer tried in his own brilliant and unorthodox way to put coincidence under the lens of the objective science, the physics of his day. However, the mythos that it represented gave little support for any effort to go beyond its own mechanistic notions of causality. It had, to use Alex Comfort's term, little empathy with synchronicity. Steeped in this mythos, Kammerer final formulation of the law of the series amounted to little more than a vague notion about the replication of similar events. It is our intention in this chapter to move beyond Kammerer and to consider synchronicity in the light of a contemporary physics, which breaks the mold of mechanistic explanations and is therefore more empathetic with the unexpected and the creative. The unbroken process. Synchronicity implies a cosmos in which seemingly unrelated events are woven together to form a continuous world fabric. Such a cosmos does not square with the classical mechanistic physics that views the universe as a loose assemblage of objects, forces, and energy. At the beginning of the 20th century, the house of classical physics was built on the strongest stuff imaginable, the impenetrable atoms, which were the basis of the physical world. The location of each of these atoms was precisely fixed, and the three-dimensional space of Descartes' geometry. In a very few years, however, the house of physics was shaken to its very foundation. The atoms of its walls dissolved into abstractions, and these in turn became probabilities written on the blackboards of mathematicians. Its location became indeterminate. The very space it occupied became curved, warped, and even filled with wormholes. It was assaulted by Einstein's general theory of relativity on the one hand and quantum theory on the other. Both new theories view the cosmos as an undivided whole, though they do so in very different ways. Beginning with Einstein, the entire cosmos becomes an undivided field. Objects such as atoms and stars are viewed as properties of this field. They are seen as local concentrations of it. Think of the vortex of on the surface water. Each consists of a stable, whirling movement which gives a unique form to that particular part of the surface. While such vortices can interact with each other, combining to form new and larger vortices and canceling each other out, they have no separate existence in and of themselves, but are simply local characteristics of water. Unlike the general theory of relativity, quantum theory does not deal with the existence of objects, but with the actions or events. It is an elaborate mathematical structure within such separate objects have, in fact, no representation. Only events have reality for the theory, and these are all intimately interconnected. For example, if several subatomic particles are involved in an experiment, they cannot be treated as separate realities. The outcome of the experiment is determined by the total quantum state of the system of particles, which cannot be viewed in any real sense as comprised of separate or independent objects. Instead, the mathematics of quantum physics treats any system of particles as part of a larger unity. Wholeness in quantum physics even includes the experimental apparatus by which measurements are made. Beyond this, it includes the entire context of the experiment, the laboratory, the experimenters themselves, and so on. Quantum physicist David Bohm has observed ultimately the entire universe with all its particles, including those constituting human beings, their laboratories, observing instruments, etc., as to be understood as a single undivided whole, in which analysis into separately and independently existent parts has no fundamental status. Microworld synchronicity. The wholeness suggested by synchronicity lies in the meaningful connections of events isolated in time and space. In spite of their separations, they seem to be linked together. Something like this is known in quantum physics, and perhaps not surprisingly, it is referred to there as synchronicity. The story of quantum... Let's try that again. So the wholeness suggested by synchronicity lies in the meaningful connections of events isolated in time and space. In spite of the separation, they seem to be linked together. Something like this is known in quantum physics, perhaps not surprisingly, it is referred to there as synchronicity. The story of quantum synchronicity, like many stories in modern physics, begins with Einstein. Though he was one of the pioneers of quantum physics, he was never a friend of it, especially as it was interpreted by two of its founders. That's interesting. Niels Bohr and Werner Heisenberg. Heisenberg. One outcome of Heisenberg's equations was the realization that the amount of information we can obtain about a particular atomic particle is limited. Put differently, we can reach only a limited degree of precision in describing such a particle. For instance, we can measure the position of a particle at any instant in time with as much precision as we like, but the result will be that the velocity, technically the momentum of the particle, will become unknown. In fact, we can measure the position or the velocity with as much accuracy as we like, but in obtaining the one we lose the other. Bohr interpreted this indeterminacy as meaning that the measurement of, say, velocity leaves position indeterminate in a fundamental way. Position no longer has any meaning whatsoever. We can put position in the same class as the sound of one hand clapping. It is fascinating to think about, but has no object of reference in the world of reality. Einstein was impressed with all this And over the years, he proposed a number of thought experiments designed to demonstrate that Bohr's thinking was incorrect, as though a thought experiment is an imaginary experiment designed to demonstrate that some aspect of a theory succeeds or fails on logical grounds alone. Einstein published the most famous of these theses in 1935 with Boris Podolsky and John Rosen. It has since become known as the EPR paradox. Einstein, Podolsky, and Rosen built their experiment upon certain subtle facts that follow from the mathematics of quantum theory. In particular, two particles that share a condition known as singulate state, for example, they may have been two halves of some larger particle, retain a special relationship with each other even after the separation and go their separate ways. If, for example, the original larger particle splits, ejecting the two component particles in opposite directions, the positions and velocities of the two remain correlated. Though one travels, say, to New York and the other to Paris, knowing the position of one allows us to specify the position of the other. The same is true of velocity. An example often used is the interaction of two billiard balls. Suppose that two such balls interact on the pool table. One strikes the other. At the instant of impact, they exist as a single particle, which immediately disintegrates, sending its component parts in opposite directions. If we measure the position of one, we can infer the position of the other similarly. If we measure the velocity of one, we can infer the velocity of the other. The positions of the two balls are precisely correlated, as are the velocities. If there were quantum billiard balls, however, they would have a very unusual property. Measuring the position of one of them would make it impossible to measure the velocity of its velocity also. This is Heisenberg's limitation. Einstein, Podolsky, and Rosen simply said, why not measure the position of one and the velocity of the other? For these two measurements and correlation of the balls' position and velocities, we can know both measurements for each ball. We can have complete knowledge of them. Einstein wanted to show first of all that Heisenberg's constraint on complete knowledge was artificial. But more importantly, he wanted to demonstrate that quantum theory is an incomplete description of reality. But considered Bohr's reply. In essence, he stated that the EPR paradox artificially separated the measurements of two particles. Making a measurement on one particle, he said, would effectively blur the frames of reference of the other. Bohr's reply implied that the particles were in fact no more independent after leaving the singulate state than they were before. This idea is holistic in that it emphasizes the notion that the two particles cannot be treated as separate objects, even though they occupy different locations in space and may in fact be quite far from each other. This remarkably holistic feature of Bohr's replies to EPR's paradox was highlighted in 1965 by the British physicist John Bell, who restated Bohr's ideas in a form testable testable in the laboratory. He proposed a set of mathematical proofs, now famous as Bell's inequalities, which demonstrates that a pair of particles, once in a singulate state, retain an interconnection despite their different future locations in space. Bell's demonstration of interconnection at a distance shifted the emphasis of Bohr's original argument towards the holistic implication of non-locality. The particles need not share the same local region of space to be immediately interconnected. Bell's inequalities deal with the spin of the atomic particles rather than their position and velocity. Spin is a formal quantum characteristic which corresponds roughly with the rotation of the billiard ball. The inequalities predicts that the laboratory measurements of the spins of separate particles which were once united will be correlated to a significant high degree than would be expected on the basis of classical physics. To date, several experiments have been conducted, and there seems to be little doubt that the inequalities are correct. The spin of such particles are indeed correlated at a distance, and apparently through no causal mechanism allowed by classical or mechanistic physics. And in quantum physics, this correlation is termed synchronicity. The full implications are succinctly stated by physicist Nick Herbert, who observed a universe that displays local phenomena built on a non-local reality is the only sort of world consistent with known facts and Bell's proof. It has been said that if you are not shocked by quantum physics, you simply don't understand it. Certainly, Bell's inequality sent a shock throughout the house of physics. One way that physicists deal with the shock is to treat the inequalities simply as a set of mathematical predictions and nothing more. This, in fact, has been a common attitude, but it has not proved very satisfying. The alternate view, developed by David Bohm, proposes that two particles are not separate at all, but instead constitute two different views of one single particle. Suppose, says Bohm, that the single particle were a fish in a tank, with two video cameras set up to view it through two separate monitor screens. Put the camera at the right angle of each other, one in front of the tank and the other beside it. What we see on the monitors appears to be two separate but very remarkable fish. Because of every motion that one makes, a correlated motion will be observed from another. Not realizing the images of the monitors are the same fish, we might conclude that they are separate, connected to one another for some unknown causal change. Bohm says that we see each of the fish read particles separately in three-dimensional space, while in reality there is only one fish particle which exists in six-dimensional space. The two are the same when seen from the higher dimensional perspective. Now, the above observations deal with the microworld of unlimited particles. Not unlimited, of ultimate particles, excuse me. It seems to us, however, that we are dealing with similar phenomena in this synchronicity experience in the middle world of ordinary day-to-day living. In both instances, we are faced with highly correlated sets of events for which there is no causal explanation, and in both instances that we actually see appears to be no more than a surface display of a deeper, unseen event connecting the separate parts. Middle world synchronicity, however, seems more complex than its microworld counterpart. In the latter, the two separate appearing particles are no more than mere images of each other, whereas in middle world synchronicity we seem to see two distinct different facets of a larger hidden pattern. Here, the surface display that we actually see might better be likened to something seen on a video game screen. The actions of the various objects on the screen are highly correlated with each other, but do not represent manifold reflections of the same image. Rather, they are all generated from a larger implicit pattern unfolding in the circuitry of the video game's computer. It is this hidden pattern that produces the seen events that fit together so smoothly. As we will soon see, this metaphor, originally suggested by Alex Comfort, is an apt description of an all-encompassing cosmological model of David Bohm has recently been developing. The holographic order. The modern physics worldwide that is more empathetic with synchronicity is the holographic order now being developed by Bohm. Unlike the cosmos inherited by Descartes, which can be imagined as a topological that's what it is, a topological map of objects and events occupying separate locations in a three-dimensional coordinate system. Bohm envisions the cosmos as a hologram. His vision is radically holistic, allowing for the creation of separate but correlated events beyond the bounds of causality. The hologram is made from a holographic plate. When viewed under ordinary light, such a plate looks much like a underexposed photographic negative. When viewed under special lighting conditions, such as laser light, it takes on an appearance of an open window, just as though a real window. We can see the entire scene beyond by looking through any part of it. In a hologram, the whole landscape is visibly contained, or, to use Bohm's terms, enfolded into each part. This makes a lot of sense with stuff I'm filming right now. I remember that one page. The essential wholeness of the hologram is that each part contains or unfolds the whole, or the cosmic scale of Bohm's theory. This means that each part of the world contains the whole of the universe hidden, unfolded within it. This stunning notion, though new to modern science, is well known in the world's mystical poetry. In the Garden of Mystery, the Sufi mystic Muhammad Shahbazari, something like that, states, "Know what the world is a mirror from head to foot. And every atom are the hundreds of blazing suns. If you cleave the heat of one drop of water, 100 pure oceans emerge from it. And in the people of the eye is a heaven. What though the corn grain of the heart be small, it is a station of the Lord, both worlds to dwell therein." Something like that. I don't know. It doesn't seem all that deep to me. The hologram is created when a pattern of light waves interactions is captured on the holographic plate. The capacity to unfold large and whole images within small parts seems to be characteristic of such patterns of interactions. An example is the pattern of ripples seen on the surface of a pond a few seconds after you toss some pebbles. These ripples create complex figures as they expand, crisscrossing over the surface of the water, each spreading from its own source where a pebble fell. If we could freeze the pond instantly, these ripple patterns would contain the information necessary to reverse the process, creating the original configuration of petals as they struck the surface. The configurations of falling pebbles, we might say, is enfolded by the patterns of the ripples. This is exactly what a hologram does, using light waves instead of water ripples. On a grand scale, we might envision the entire cosmos as a vast light pool with ripples spreading and interpreting and creating complex patterns of interactions throughout. Certain of these patterns may seem relatively stable, others may not. They may give the appearance of stable configurations in motion. This is the vision of the hollow movement at the heart of Bohm's concept of a holographic universe. Normally, says Bohm, we think of the universe as comprised of more or less solid objects such as atoms or stars, many of which emit light and other forms of electromagnetic radiation, radio waves, gamma rays, and so on. The space between objects is filled with a constant flow of radiation. Ordinarily, we do not take much account of this ocean of electromagnetic waves. Instead, we consider solid objects to be real and flux of energy to be a secondary influence. But Bohm flips this picture upside down, making flux the primary reality of the cosmos. He views solid objects as stationary patterns of wave interactions that emerge out of the hollow movement rather than points of primary reality. Most of us have seen analogous examples of wave interactions and the tiny stationary patterns of ripples on the surface of a cup of coffee or tea when the table is set into vibration, perhaps by a larger motor rather running nearby. These small standing waves formations are the product of a less apparent but more basic action of ripples flowing swiftly about the surface of the cup, reflecting off the walls and interacting with each other. This is analogous to Bohm's notion of how solid matter is generated out of the flow of electromagnetic waves. As Einstein and the general theory of relativity has viewed objects to be stable configurations of the space-time continuum, so Bowman's view objects as stable patterns of motion. With the vision of reality, Bohm hopes to unite relativity with the other great cornerstones of modern physics and quantum theory. The universe, according to Bohm, actually has two faces, or more precisely, two orders. One is the explicit order, corresponding to the physical world as we know it in day-to-day reality. The other, deeper, more fundamental order, which Bohm calls the implicit order. So we have the explicit order, and then we have the implicit order. Explicit implicit order. The implicit order is the vast hollow movement. We see only the surface of this movement as it presents or explicates itself from movement to movement in time and space. What we see in the world, the explicit order, is no more than the surface of the implicit order as it unfolds. Time and space are themselves the modes and forms of a unfolding process. They are like the screens on the video game. They display on the screen. The displays on the screen may seem to interact directly with each other, but in fact, their interactions merely reflects what the game computer is doing. The rules which govern the operation of the computer are, of course, different from those that govern the behavior of figures displayed on the screen. Moreover, like the implicit order of Bohm's model, the computer might be capable of many operations that are in no ways apparent upon examination of the game itself as it progresses on the screen. The notion that implicit order is important to our understanding of synchronicity. The notion of implicit order is important to our understanding of synchronicity because it shows us that the cosmos contains possibilities different from and greater than we had suspected. Descartes' universe, for example, is limited to the idea of locality. Events must be near one another to be related. But Bowman's picture of the implicit order is that of a vast scintillating hologram. Scintillating, I guess. As much it shares an important feature with all holograms, one with which we are always familiar. Each part contains or unfolds the whole. Localities does not have primary significance here, as the whole is entirely unfolded in each part. Locality is a property of the explicit order and not of the deeper implicit order from which the explicit order unfolds. Let's see. I want to see something for my own learning. everybody thinks. So I can't afford to care what everybody thinks. I have to do this for the MS, and I'll have to push myself to do this, even to the degree of great embarrassment. But I have to do it. I have to do it because I can't let it just absolutely defeat me. I'm sure there's plenty of people who don't give a shit, but I do. First of all, let's make sure I pronounce it right. Scintillating. Of course it's scintillating. Why am I saying it's... See, it's silent, so... Scintillating. Okay, in our ordinary way of seeing, we have perhaps over-related the importance of locality as something of primary significance in and of itself. Bell's inequalities would suggest this. Like many other regularities observed in the natural world, locality must be important under certain fixed conditions, but not under others. For example, the appearance of meaningful patterns of events such as those seen in synchronicity, patterns which are not connected by local chains of causality, become possible in the holographic worldview. According to Bohm, what is more important than locality is the degree of unfoldment shared by apparently separate events, and this way events separated in space or time can share a more essential relationship than other events which may be physically near each other. Two persons who even at a distance share a common thought and feeling have more in common than this regard than do two who are near each other, who are even perhaps engaged in conversations with each other, but do not share a common state of mind. Notions such as these, which run directly against the grain of mechanistic science, are strongly empathetic with synchronicity. Indeed, as we know, synchronicity often involves a coincidence of separate events that seem connected in a way that makes sense only outside the usual limited ideas of causality. The pattern that repeats. Before we return to Bohm's idea regarding the holographic universe, let us take a side excursion to examine some coincidences that involve repetition. We will meet Rupert Sheldrake, a British biochemist who indeed meshes with synchronicity and holographic perspective, and Ervin Laszlo, a Hungarian systems theorist who has developed similar ideas in terms of quantum physics. Perhaps the most common type of synchronistic experience, and the type Kammerer focused on almost exclusively, involves the idea of theme or pattern of events that repeats itself. It can be named a number, a topic of conversation. It can be a name, a number, a topic of conversation, an idea, an item of clothing, or just about anything. Recently, for example, one of the authors was talking with a friend about Sheldrake's theories, discussing possible relationships to Bowman's notion of the implicit order. He happened to have a written transcript on the conversation between Sheldrake and David Bowman, which he loaned to his friend. The latter read it while listening to the local public radio station. The station happened to be airing one of the series of interviews titled Physics and Beyond, and he found himself listening to the interview with David Bohm, in which he was talking about Sheldrick's theory. A variation on the theme involves an actual appearance of something that previously existed only as a thought or idea. The arrival of the scarab beetle at the time a young patient was relating her dream of this insect is a case in point. So are many instances of Arthur Koestler's library angel. His tongue-in-cheek spirit associated with lucky coincidences involving libraries, quotations, references, and the like. An excellent example of the angel at work was reported to Koestler, is that what it is? I guess it is Koestler. In 1972 by Dame Rebecca West, who was researching a specific episode to look that took place during the Nuremberg war crime trials. And I looked upon the trials in the library and was horrified to find they are published in a form almost useless to the researcher. They are abstracts and are cataloged under arbitrary headings, of course. After hours of research, I went along the line of shelves to an assistant librarian and said, I can't find it. There is no clue. It may be in any of these volumes. I put my hands on one volume and took it out and carelessly looked at it, and it was not only the right volume, but I had opened it at the right page. Koestler comments that the coincidences of the library angel type are so frequent that one almost regards them as one's due. An instant of repetition system synchronicity, which involves three elements. The third order coincidence, according to Kammerer's classification, occurred to one of the authors while he was driving across town. He noticed that the car radio was playing an old popular song about bad Leroy Brown, who, among other things, is said to be meaner than a junkyard dog. The phrase stuck in his mind. He imagined that there must actually be such a dog living out their lives in a junkyard, growing older and meaner as by the day. These reflections were cut off abruptly as he switched stations. Instantaneously, he heard an advertisement for a local junkyard billing itself as home of the junkyard dog. He happened to look up and notice that he was passing a large junkyard. The sign read, Home of the Junkyard Dog. Okay, we're super red. How you doing, Chase? How you doing? These cases involve common themes and These cases involve common themes or ideas that keep cropping up either in written form, in thought, or in concrete reality. Quite simply, there is in each instance a pattern that repeats. That might be a good place to stop. My back is burning. My shoulders are burning.